once more. My name is Radina Belova. I'm Regulatory Vice President with the Interstate Renewable Energy Council, and I welcome you to today's workshop. So I think we've got critical mass here. Let's go ahead and get started. All right, so we will be accepting questions in the chat throughout today's presentation. Please don't hesitate to drop them in there, and we will have a couple of stopping points throughout the presentation to address questions, so we will not be holding them all for the end. First and foremost, we would like to thank the Department of Energy's Solar Energy Technologies Office for their support of this project, and provide a little disclaimer here that this material that you'll be hearing today is supported by the DOE, but does not represent the views of the DOE or the US government necessarily. And a little bit about the Interstate Renewable Energy Council. IREC focuses on building the foundation for the rapid adoption of clean energy and energy efficiency to benefit people, the economy, and our planet. And an overview of our agenda today, we're going to begin with an introduction to the batteries project and the energy storage interconnection toolkit that serves as the foundation of today's workshop. Then we'll dive into an overview of what are technical standards, how are they made, what are the primary challenges and solutions. Then we'll dive into the technical standards relevant specifically to energy storage interconnection. And in part 3, putting it all together, we'll talk about how technical standards interact with interconnection rules and regulations, how processes can be affected by standards updates, and the standards adoption process, how states can adopt the latest, most updated technical standards. And we'll close with a look at upcoming trainings that are part of the series focused on energy storage interconnection. A little bit about the batteries project itself. Batteries stands for Building a Technically Reliable Interconnection Evolution for Storage. This is a 3-year project. In year 1, we scoped out the issues that we subsequently addressed in the toolkit of energy storage interconnection solutions. We began with a list of approximately 40 storage interconnection issues and had to whittle that down, because clearly that is a very large number to develop solutions for in a year. We landed on 8 storage interconnection issues that we then developed model language for, model interconnection procedure language, as well as other resources and solutions that regulators, utilities, storage developers, and other stakeholders can use. These are meant to be meaningful, accessible, usable solutions to energy storage interconnection challenges, to the 8 barriers addressed in the toolkit. The toolkit was published in March of this year. It is available on IREC's website. Perhaps we can drop a link to the chat for anyone who hasn't had access to it yet. And we're now in year 3 of the project. So this workshop is part of a series of 4 workshops and 8 trainings focused on conveying the solutions contained in the toolkit in a way that allows you all to ask questions and to dive more deeply into each of the toolkit chapters and challenges. And I do want to note we have an amazing team of partners working on this project. IREC is the project lead, and we're working with the Electric Power Research Institute, Solar Energy Industries Association, the California Solar and Storage Association, the New Hampshire Electric Cooperative, Pacific Core, and Schutt, Mahaly, and Weinberger. And the idea behind bringing this project team together is to have diverse viewpoints come together to develop consensus-based solutions on these often very complex energy storage interconnection challenges. And that is an overview of the project. And with that, I'm going to hand it over to my colleague Gwen to share a little bit more information about what happens with the professional development hours.
Thanks, Radina. For those of you who saw that IREC is offering professional development hours for today's session, you'll have noticed that there was an option in the registration form to indicate that you wanted that. If you did indicate that, then IREC will follow up with you after today's session. We are tracking how long different people are in the session, and we'll use that as the basis for how many hours you are eligible for. So you'll receive a certificate from us. And one thing that I would ask is if your name as it's displaying currently in the event is not identifiable, like if it doesn't include your first and last name, please update that. That will help us to ensure that we are appropriately tracking the time that you spend in today's session. And just so that everyone is aware, we will not be offering additional PDH for views of the recorded event.
All right, thank you so much, Gwen. And with that introduction to the batteries project, I will hand the presentation over now to my colleagues, Midhat Mafazi and Brian Leidick. Take it away.
Thank you, Radina and Gwen. I'm Brian Leidick, Chief Regulatory Engineer here at IREC. And I don't know if we've got the Poll EV or Poll Everywhere working yet, but if we do, and once we do, there's one more poll for you, which is how much familiarity do you currently have with grid interconnection standards, being basic, intermediate, or advanced knowledge. And we're talking about technical standards here, those that get used and referenced by grid interconnection rules, but not the interconnection rules themselves, just to clarify there. So we're going to start at a pretty high level overview of what standards are. And the batteries team looked at standards that, technical standards that relate to interconnection rules. And we're just going to start with what is a standard, just for folks that aren't that familiar with technical standards. The idea is that by the time we're done with today's presentation, you'll have a good idea of what standards are and how they relate to interconnection rules. And in the technical training coming up next month, we'll dive deeper into those standards. And just a reminder, we are looking at standards that are related to distributed energy resources, meaning they're connected at the distribution level only. So first off, what are standards? Standard is a formal document that establishes uniform engineering or technical criteria, methods, processes, and practices. Something like, computers, electrical outlets, vehicles, they all utilize these technical standards in lots of different industries. Almost every industry uses technical standards. And they can support certification for products to provide compliance and interoperability. And they can help reduce unnecessary burden and cost on manufacturers and consumers that would come with having to comply with differing requirements across jurisdictions, say. And they generally get revised as learning and improvements are made in the industry. So, most standards, they're living documents, and they need to be revised and adopted. All the revisions need to be adopted over time. And some examples of standards that you're probably familiar with from your day-to-day life, or Bluetooth, or USB ports on a laptop. As well as martinis. The American National Standards Institute also has a code for martinis that we'll reference here a little bit. Let's go to the next slide. Thank you. So standards are generally developed through a consensus process and published by any number of standards development organizations. And consensus process usually means that there are a number of different stakeholder groups represented in the working group creating the document. And under the generalized term standard, there are also recommended practices and guides, but only standards contain mandatory requirements, and those predominantly use the word shall. You shall do something, whereas a recommended practice is preferred but not optional practices, basically, or preferred but optional practices. And guides present alternative approaches with no real clear-cut recommendations on which way to go. So standards are generally voluntary, but they may be enforced by references to the standards in rules or laws. And on the right, we've got a typical structure of a standard, this is the Martini standard again, with the scope of application up top, so you understand, what the standard applies to and what it does not. And then there's generally definitions that are required to understand the standard, and general notes or requirements up front. And then the main technical content is followed by annexes. And on the right, you have that general contents laid out there. Testing procedures to verify conformance to the requirements may appear as well as they have here in the Martini standard. or they could potentially be omitted or in another standard. Next slide, please. So consensus standards are typically created by working groups, but the structure of the working group is dependent on the standards development organization or the standard itself. And like I said, there you have representatives from different stakeholder groups participating to represent different viewpoints. And proposals are generally, they're put forward by any number of people. You might start with a straw man proposal that someone has drafted, or you have a bunch of subgroups working on different topics. And so that starts as a proposal, and it works its way through the working group, and eventually you get a draft. And usually, working group goes through a number of drafts before it goes to the voting process, or balloting process, as it's sometimes called. And so then that final, or initial draft, I guess you'd say, the ballot-ready draft, is then voted on by the working group or by a ballot committee, depending on how the development organization does it. And there may be several rounds of voting and then commenting by voters, and then addressing those comments from the working group before publication, as long as it does get approved by the balloting pool. And standards development organizations have their own rules on how often a standard can or must be revised, and some standards become inactive over time. So, if something is sat for 10 years and hasn't been worked on, then it may be considered that it's not active, though, it's still out there in the world. It just shouldn't be referenced anymore. Next slide, please. So for standards that do have test specifications, there's nationally recognized testing laboratories, or NRTLs, or NERTLs, as they're called, and they can offer conformance testing for products and to any number of different standards. The logos of a few common ones that are used in the DER world are here. These are ones that are accredited to offer testing to the UL 1741 standard, which we'll talk about a little bit more. And the NERTLs are accredited by OSHA to test specific test standards. So if you go to OSHA's website, you'll see a list of all the standards that any NERTL is able to apply and offer certification for. NERTLs have their own lab equipment where they can test products, or manufacturers might choose to have them tested at their own facilities. So you can see in the middle there, any NERTL can offer basically 3 different ways of testing at their own lab, at the manufacturer's facilities, where they're witnessed by an engineer, and that's called witness testing. Or some manufacturers can be approved by the NERTL to run their own testing and basically give the reports to the NERTL engineers, and that's called supervised testing. So it's a little bit more hands-off and can happen a little bit more quickly. Usually kind of the longest process is to send your equipment into the NERTL, to the NERTL's laboratory themselves, and then probably the easiest is to be supervised testing. But any one of those pathways might be utilized at any time, and you can get certified products. And once the product is certified, then the NERTL puts its certification report on a list, and which is generally on the website of the NERTL, and then the product is then listed. Next slide, and I'm going to hand it off to Midhat for this one.
Hi there, Midhat Mafazi. I'm a regulatory engineer with IREC. So one challenge the batteries team took on was that standards develop and change over time, but interconnection rules can lag, and many such rules haven't yet incorporated updated standards that could support energy storage integration. It's important to understand which standards are relevant for energy storage and how to adapt the element of those standards into interconnection rules and practices. Next slide. So Chapter 8 of the toolkit took a deeper look at existing interconnection rules and identifies relevant standards for energy storage systems. The exercise considered over 80 documents, standards, guides, and recommended practices that touch on ESS. At the end, when it comes to interconnection matters, it all boiled down to 3 relevant standards, which are shown on the slide. the 1547 series, the UL 1741 and its CRD, and the IEEE C62.92.6 for grounding practices. Over the course of this workshop, we'll be going into more details on these three and point out the relevancy of each in interconnection rules. I do want to mention one item before jumping into the standards. Most ESS are inverter-based, so many of the elements that we are talking about today apply to inverter-based systems. Therefore, where we talk about DR standards or inverter-based standards or ESS standards, we're essentially talking about the same thing. Next slide. So that concluded part one of the workshop, and we'll now jump into the each of the standards. And so we'll go through the 1547, the CRD, and the C62.92.6. And we'll start with the 1547. Here's a quick overview of what we'll go over in this part. The most important technical standards for interconnection of DER is IEEE 1547. It contains the technical requirements that apply to a DER system connecting to the grid. IEEE 1547 is titled as Standard for Interconnection and Interoperability of Distributed Energy Resources with Associated Electric Power System Interfaces. The standard is written into law for distribution utilities to base interconnection requirements on 1547 through the Energy Policy Act of 2005. Next slide. So in terms of evolution, the standard has been around for many years now. It was first published in 2003 and contained 15 pages of technical requirements addressing many topics, including synchronization, islanding, response to faults, voltage or frequency excursions, and power quality. Initially, it was expected that due to their low penetration, DERs should simply trip and disconnect from the grid when anything abnormal occurred. Voltage and frequency trip settings were selected to avoid interactions with the grid, and the DER wasn't supposed to attempt to regulate voltage. By about 2012, it was becoming clear that DER, especially in the form of solar PV, were becoming a larger share of generation on the grid and needed to be relied upon during abnormal conditions. California was considering how to adapt smart inverters which could support the grid. 1547 was amended in 2014 to allow for greater ride-through capability and allowing for the DER to regulate voltage without requiring it. That is why you see the shift in language from shall trip, shall not regulate voltage to may ride through, may regulate voltage. Eventually, in 2018, the standard was completely revised and the technical requirements were expanded to 94 pages in the document. New requirements include ride-through, voltage and frequency regulation to support the grid, as well as supporting communications and control in a standardized manner. As shown in the slide, such smart requirements are referred to with the word shall. Next slide. So IEEE 1547 is complemented by a number of other standards, guides, and recommended practices which address the element of 1547 and related DR issues. What you are seeing on the slide is a list of supporting documents. Some people refer to this as the 1547 family series of standards. These supporting documents also get revised from time to time, typically once the base standard is updated. The 1547.1 is a long document that specifies tests to verify conformance with the base standard 1547. The document was published in 2005 and then updated in 2020 following the updates to the base standard. The DAT2 is application guide. The DAT3 is a draft guide that details cybersecurity. When you see the letter P before 1547, it just means it's still in the draft stages. Anyways, the intent here is not to review each of these, but it's to just make you aware of these complementing documents within 1547, some of which are in the process of revision. Before moving on, I will perhaps highlight the last one on the list, 1547.9, which details guidelines on how to use the BESS standard in terms of energy storage systems. The .9 was introduced to bolster ESS content that was missing in 1547-2018, and also provides guidance for EV charging stations with vehicle-to-grid capability, V2G. The batteries project team carefully evaluated and considered all the inputs encompassed within the .9, even while in its draft stages. Next slide. As I mentioned, the 2018 version includes 90-some pages on technical requirements for DERs. What you need to know is that there is no one way to apply the standard, which makes it a little harder to adapt compared to the 2003 version. The standard provides a menu of items to select. This includes the level of write-through, category 1, 2, or 3, reactive power capability, category A or B, communication protocols. Similarly, the use of voltage regulation is optional. By default, voltage regulation is not activated. And depending on how voltage functions are deployed, there is potential for DER customer impacts through curtailment functions. Next slide. The default setting for 1547-2018 is unity power factor, no reactive power from DER, meaning products will come off the shelf to provide no voltage support. So states and utilities will need to consider whether or not to turn voltage regulation on by default and which functions to use. Also, some functions are mutually exclusive, meaning only one can be turned on at a time. And some functions have the potential to impact customer finances. So you may want to address that when adapting the standard. We intend to spend more time on this in the future training. Next slide. Here we wanted to share the various practices in terms of how the updated 1547 standard is referenced in interconnection rules. In terms of implementation practices in interconnection rules, EPRI has 3 defined ways where jurisdictions can implement. There is the general reference where you don't repeat elements or clauses of the standard. There is detailed reference where you reference clauses from the standard. There is the full specification language by clause, where you have clauses in your own language in the rule. Basically, the full specs is almost like you are duplicating the standard, meaning you do not need to buy the standard if you're looking at the technical specs within the rule. Obviously, there is benefit and risk to each of these approaches, so it is important for stakeholders to agree on the approach. Here are also examples of how some states have gone through around the reference this far. Minnesota has detailed reference on technical requirements, has the constant power factor and volt-var as default, and listed communication capability. Maryland issued compliance date and are still working on the technical requirements. Hawaii has the general reference to the standard in the rule, but then the SRD provides Hawaii-specific requirements. California has the full specification, but arguably there are some elements that look more like a detailed reference. I will also say that for all these states, at least for inverter-based systems, they are following category 3 for write-through and category B for the reactive capability. And California is the only state that has specified COMS to use the 2030.5 protocol. All other states only require COMS capability without defining specific protocols. Next slide. Here's a general overview of what to consider when adapting 1547-2018. We'll go into details in the training on this. and batteries goes into details about aspects of these topics. Basically, you're going to need to determine a timeline for implementation. You will need to decide where the technical requirements will end up. Is everything going into the rule, like Rule 21? Or will some technical requirements go into utility handbooks? Similarly, category selection for normal and abnormal performance will need to be considered. I'm not going to go over each of these boxes you see on the screen. And certainly, based on IREC's experience in other states, even 3 hours on this topic won't be enough for us to discuss this. There's just a lot of consideration that needs to go into each of these boxes on the screen. The good news is that IREC has developed a decision option matrix that goes into each of these boxes, gives you the justification for each, and guides you through the near-term, mid-term, and long-term decisions you need to make in your own jurisdiction. During the training, we will showcase this matrix and hand it to you so you can
So
use.
did he come by and you didn't have anything out there?
Sorry, if please mute yourself if you're in the audience. And if we need to do that on our end, Gwen, let's please go ahead and do so. Thank you so much.
Don't worry about it, darling. Why don't we?
During the training, we'll showcase this matrix and hand it to you so you can use it wherever you are in this adoption process and tailor it to your local needs. Next slide. So finally, here are some recommendations on 1547. We will dig into the details of these recommendations from the batteries report in the training. Many technical requirements in 1547/2018 can affect energy storage performance, and states or utility interconnection rules should fully align with the way they are stated in the standard. Due to a number of detailed options on how ESS systems implement the standard requirements, the report recommends that the application forms designate these details. I will touch on the RPA designation later on today, but we will be going into more details with the application forms in the training. So you have the limit active power implementation, volt watt implementation, grid services. All these are items that can be designated in the application forms. Along those lines, one-line diagrams would be helpful for all system sizes to ensure all optionality is specified in a way the utility understands. Next slide.
All right, and we now have a moment here for questions before we go into the UL CRD. Let's see here. Do we have any questions in?
Do we just unmute ourselves to ask the question?
Please go ahead, and we'll also definitely make sure to get to folks who have posted questions in the chat as well.
Great, thank you.
Mm-hmm.
Yeah, so I had a two-part question. So you had mentioned that California is the only state that adopted comms requirements. Why is that? And will other states follow suit? Why or why not? And then the second part of my question, what does the rest of the world standards look like and what are they following?
Yeah, so definitely, California has provided more details on the requirements, and they listed, as you mentioned, the 2030.5. That 2030.5 is reflected in 1547, is one of the three protocols that is listed within the standard. Most of the states are waiting to adopt 1547 and then maybe formulate some kind of pilots or try to figure out which of the three protocols they are more comfortable with in terms of defaults. And that could be based on sizes for different DRs. It could be the smaller system will be using 2030.5, a larger system, the DNP3. But I'll let my colleague also chime in to relay other experience and what other states are looking into.
Yeah, California's definitely gone the farthest in terms of they've not only determined which protocol that they'll use 2030.5, but also created a implementation guide called the CSIP California. Well, I forget what the S stands for, but they have an implementation guide on how to use 2030.5 for their own requirements. Although their requirements are in line with 1547, there's some extra implementation stuff to keep in mind in terms of if you were going to connect to a communication system, how you would register and such, and how those commands are taken. So they've done a lot of work in that regard, but even they still aren't ready to implement 2030.5 to DERs. So today in California, only systems larger than 1 megawatt require communications, and they're not really using the 2030.5 necessarily, or the 1547 required capabilities of inverters just yet. And so there's a plan to over time integrate that and require communications to smaller systems as well. But really, there's just a lot to be figured out. And so California, has kind of roadmaps in mind, and other states who are really just starting to adopt the standard need to create those roadmaps to figure out exactly how things are going to be implemented over time.
Great, thank you, Midhat and Brian, and for the great question. Well, I think we have time for one more, and then we'll have additional opportunities for questions. So I'm just going to go down the chat. Ruda Pollard, I see a question from you. Are there any mobile apps that can be used to streamline knowledge of requirements?
Not that I know of. There's if you want to find out everything that is required, you have to go to every single different state or utility, find out what standards that they have in mind, or what standards they're referencing, and I'm not entirely sure exactly what level of knowledge we're talking about here, but really, there's no central database that I can think of that really contains, everything related to interconnection standards.
Thanks, Brian. And Rita, I see your follow-up comment. I don't think it's a strange question at all. We have Solar app for permitting. It would be amazing if we had something similar for standards where you could go to one place and get all the information that you need. So here is a call out for anyone working with the national labs to suggest this kind of project. This could be a really valuable resource. So thank you for asking. And Nancy and Ashok, I see your questions. Drew as well. We will make sure to get to your questions in the next break for questions, which will come up shortly. All right, so let's move on with the next slides. All right, take it away.
Okay, and I'll also note, we did get results from that first poll, and it looks like we have 31% of folks here have basic familiarity with technical interconnection standards, 56% on intermediate, and 13% advanced. So happy to, again, this is a fairly high level overview for folks that want more detailed information. We will be having the detailed training next month, but also feel free to use that Q&A to get to any details that we're not getting to in the presentation here. So a little bit about UL 1741 and the Power Control Systems CRD. 1741, the title of it is the Standard for Safety, Inverters, Converters, Controllers, and Interconnection System Equipment for Use with Distributed Energy Resources. So it's the main standard for inverters, which are the main interface between renewable energy DER systems and the grid, as well as some non-renewable energy systems on the grid, but widely used in DER, and tends to be, it's not only used for interconnection purposes, but also for National Electrical Code compliance as well. So it's a very broad standard that covers personnel safety. You can go to the next slide here. So it covers personnel safety, property safety, fire safety, and it's widely used as well as for balance of system components. So the inverters and other portions of PV systems or turbine systems, some of those can be listed to UL 1741 as well. And then we'll talk about power control systems more specifically, which is kind of a newer type of balance of system item that integrates with the interconnection system on inverters. But 1741 was initially published in 1999 and had updates in, I think, 2005 that required interactive inverters to conform to IEEE 1547-2003. And then the test standards for 1547, which is 1547.1, and that was published in 2005. So really the first time 1547 was implemented, it was through UL 1741 for the certification of inverters, and UL has maintained that throughout the last 18, 19 years, however long that's been. And there's strong familiarity, therefore, with 1741 amongst the utilities and utility engineers over many years now, allowing certification of inverters to be trusted as the main means of verification of compliance with 1547. So it makes it fairly easy if you've got a certified inverter being the interface to the grid. The utility, at least in the past, hasn't needed to check much else about the system to determine that you are in compliance with 1547 because the inverter itself ensures that compliance. Then Supplement SA was created in 2016 to test grid support functionality, which is for quote-unquote smart inverters, and has been used in places like California and Hawaii since 2017. They've required that SA certification since 2017, and that is based on the old version of 1547, either 2003 or there was an update, as Midhat mentioned, in 2014, an amendment allowing for greater ride-through and voltage regulation and whatnot. But the reason SA was created was because we didn't yet have IEEE 1547 2018. And so this was kind of a way to get smart inverters to market earlier than waiting for IEEE 1547 to be updated. And so it was based on, there weren't actual requirements for smart inverters in 1741 SA. They relied on what they called SRDs, or source requirements documents, which would have been found in Rule 21 in California. And then for Hawaii, there's HECO's Rule 14H. And those served as the basis of the requirements. And then there were test protocols inserted into 1741 in this supplement SA. And a lot of the test protocols that eventually would go into 1547.1-2020 to support 1547-2018 were based on those initial tests in 1741 SA, but there's a lot more in 1547-2018. And then once 1547 2018 and 1547.1/2020 came along, that required a new revision to 1741 to allow inverters to be certified for 1547-2018. And so that was Supplement SB was created. And it was initially published in 2020, soon after 1547.1 was published. But there were quite a few kind of issues and holes in 1547.1 that were discovered as people tried to start utilizing it for testing, and that required a lot of extra material to be created. And so 1741 kind of used the Supplement SB to patch some of those holes and republished it in September of 2021. And so really, there's one reason we don't have many certified products for 1547-2018 yet on the market is because there was this big delay between 1547.1 being published and UL 1741 SB being published with these updates necessary to get everything tested in the same way. And so that new version, so that is also edition 3, and it's just good to realize that once those additions to SB were published in September, they changed the edition of UVL 1741 from edition 2 to edition 3 to make it easy to determine what version of the SB the products were tested to. So just to make sure that everything's in compliance with the newest requirements, it should be compliant with edition 3 then. And then there is a forthcoming supplement SC, and so you can see that these supplements have started to become used for adding on requirements that weren't there before and adding some optionality in 1741 to comply with different things. And that is to support, SC is to support V2G AC systems as envisioned by the SAE standard J3072. So I think it'd be, Medat could explain more about that if there's any questions about that. But that's more related to vehicle to grid, not so much what we're dealing with today. And we can maybe share some more details on the training next month if necessary.
Yeah, but Brian, I can just go ahead and maybe, I think this is the only place we mentioned the J3072. So that's, if I may add, the SAE that's from Society of Automotive Engineers, and that J3072 it's interconnection requirements for onboard grid support systems. And what it does is that it supports requirements, it's testing, I guess, its requirements are intended to be used in conjunction with 1547 and 1547.1, and it can be used for the new standard or the older standard 2003. In terms of split between the V2G, DC, and SE, pretty much the practice today is that SA and SB can be used for the V2G DC, and this new one, SC, is intended to be used for the other configuration as identified there, V2G AC. Thanks, Brian.
Thanks for that, Medat. Why don't we go to the next slide here? So onto power control systems. So power control systems are kind of just a part of a DER system, or potential part of a DER system. Not every DER system is going to include them, but it's kind of somewhat of a new concept within the last several years to have systems or devices which limit the current or the export or power of a system to a programmable level. And they're generally composed of a controller with sensors as well as inverters. And those may be in separate devices, or you could potentially have everything contained in the same space, same product. And really, these can be used alone or in conjunction with other means of controlling export. Like we've previously had utility grade relays, which can trip a DER off if it exceeds a certain level of export. But power control systems are generally very low cost devices compared with relays, and they can be certified, which makes them, desirable in terms of trying to allow them to be used in interconnection processes where it makes verification of their capabilities very easy through certification. And so 1741 has created a way to test for these things, which we'll talk a little bit more about here. And they have been used for DERs with or without energy storage to limit their output. If you just have a PV system, then limiting your output could potentially be just clipping your PV output energy. So that doesn't necessarily make as much sense as it does with an energy storage system. So energy storage systems are very controllable in nature, and they can be certified, potentially along with other components to be a power control system. And energy storage systems really allow you to manage your export level if you are paired with a PV system. So we think that there'll probably be more certified power control systems coming onto the market, especially as we see more and more energy storage adoption or PV plus storage adoption. And let's see, so one way these have been used in the past is for, or are used currently, are for tariff compliance. So at net energy metering tariffs generally don't allow you to import power from the grid to an energy storage system and then export that and get net energy metering credit for it. So oftentimes, one way for a utility to verify that you're not doing that is to constrain the energy storage system from either importing from the grid or exporting to the grid. And so that's one way these systems are used today. So they kind of have two, well, they actually have multiple use cases. There's the limiting export to the grid. There's limiting your export or import to the energy storage system for tariff compliance. And then they can also be deployed in the National Electrical Code scenario in terms of managing the amount of current you're applying to conductors or bus bars. And so 1741 kind of takes a look at all three of those use cases. Let's go to the next slide. So here we've got an example of a power control system, which can be configured in many different ways. And as I mentioned, these can be multiple pieces of equipment, or maybe you've got a power control system, an inverter that is all self-contained. But usually you've got CTs, current sensors, that are monitoring export. And this is in the export control use case here, rather than the National Electrical Code type of use case. So we're just monitoring export to the grid through the meter there on the right. And you've got a controller which monitors that current level, the export level, and then connects to the inverters, usually through some sort of communications signal to control their output. And this is an example that we would have for a non-exporting system. So we can just imagine that both the energy storage and PV systems are set up so that they only feed local loads here. That's not a terribly typical scenario. You could also manage that export level to a certain non-zero value that maybe be constrained for interconnection purposes. So in the lower right corner, you can see there are currently 8,000 watts of loads here. And let's say a large load like a clothes dryer turns off, dropping the power to 4,000 watts. Just like that. That introduces inadvertent export, as the energy storage and PV inverters, they continue to produce the same power for a moment that they did before, but less of that power is now fed to the loads. So the power control system measures that inadvertent export. So here the controller would be measuring that and then sending signals to the inverters to reduce their power. And they do so until there's no longer any excess export. And the typical response times of these systems to reduce that power back to zero or back to no inadvertent export are on the order of several seconds. And they can be less than 2 seconds. So they're not extremely fast acting, but they can be fairly fast acting in terms of other grid interactions. Let's go to the next slide. So the certification requirement decision, as it's called, for power control systems was published in 2019. And this is a certifications requirement decision is kind of like a fast testing protocol that can be produced by UL that doesn't go through the entire standards process like everything else in 1741 does. And so it's usually used for requirements that are needed on the market when you need a test standard to test to, but something doesn't exist, then they can release a CRD fairly quickly, and then those requirements are typically then go through the full process, which is usually much slower, to get incorporated into the standard itself. So this is kind of a standalone document, and they produce other CRDs. So we're just going to focus on the power control systems CRD, and it allows you to certify these power control systems for non-export, limited export functions, and as I mentioned before, they can be certified for that National Electrical Code use case for limiting currents on a conductor, as well as the interconnection use case and limited export. And then there's the import limiting and other optional modes can offer NEM tariff compliance. So there's you can export limit from all sources, or export limit just from the energy storage, or import limit to the energy storage, and all the four different modes. Then there's export only, import only, there's unconstrained, and then oh gosh, there's I think there's one more. I'm not sure what I'm missing there. But the CRD does have a path, to be included in 1741. We would hope, maybe by the end of this year. So the 1741 working group has a lot of work to do on its hands. But as the use of power control systems is becoming more, is growing more widely, we do think we'll have the requirements, the test requirements within the standard itself in the fairly near future. But it is the certification requirements decision is being used today to test these systems. And it's been written into some interconnection rules already, with the idea that we'd eventually be using the 1741 standard itself. And then for tariff compliance, I think this is also being used in some locations. Let's go to the next slide. So the key recommendations in the batteries report in terms of relating to 1741, they're mostly focused on this power control systems, CRD. And for one, we'd like to ensure that power control systems are appropriately addressed in procedures, so in the interconnection rules. And so basically to allow the use of them for export limiting. And those procedures should require certified power control systems. There could be allowances for non-certified power control systems, because you might have systems, or you might have inverters with other components from differing manufacturers, which might make it hard to get it certified. But utilizing certified power control systems makes it a lot easier to put this through a more simplified process of review. And those two items we're going to deal more with in our storage flexibility trainings and workshops coming up. So keep an eye out for that. We'll focus more on how PCS can be applied in interconnection rules. But another point is manufacturers should be listing the supported exporting and importing modes, so that the customers can relay this information on the application form to the utilities. And a lot of the recommendations coming out of this in our batteries report is to revise the interconnection forms to ask whether a power control system is included in the DER system design, and ask for details about how it's being implemented. We'll go through more of those details in the training. And then power control systems should be identified in the one-line diagram, of course, along with everything else. And it's also important to understand there's many different configurations, and with multiple inverters, even with multiple power control system elements. So understanding exactly how and where those power control systems take effect is important. And I think we are ready for a break here. Is that right, Dina?
Yeah, so I think we can go ahead and take a 5-minute break at this point. I know everyone is in different time zones, so why don't we return at 4 minutes past the hour. Whatever your time zone in, we're coming back at 4 minutes past the hour, and we're doing this little break just because we are covering quite a lot of dense technical information today, and we still have quite a bit of ground to cover after we return. So again, we will see you back 4 minutes past the hour. Thank you.
Yeah, thank you.
All right, we are 4 minutes past the hour and ready to get restarted. I hope y'all had a nice chance to stretch, take a little break. So we are now moving on to the next set of standards. Let's make sure the team is reconvened again. Everyone ready to go? All right, let's give it just one more minute. Tom, if you're speaking, you are on mute. Apologies, folks, for a little technical glitch here. Give us just 1 second. Tom, you might be double muted potentially. Gwen, do you think you might be able to help him out with that? I'm not quite sure how to handle that. Let's see here.
Yeah, Tom, I'll message you directly.
I can try to get started here.
Thanks, Brandon.
Yeah, and hopefully Tom, who's the expert, will be able to join us here. We're going to talk a little bit about IEEE C62.92.6, which is the guide for grounding current regulated resources, and which is really talking about how to ground inverters. And this is a somewhat newer standard that is kind of still working its way through recognition, for our stakeholders and utility engineers and whatnot. Let's go to the next slide here. So this is C62.92.6, basically deals with how inverter-based systems can be effectively grounded. And this starts to get a little bit technical, so I apologize if this is a little bit in the weeds, but effective grounding basically means that a portion of the distribution system, basically, a portion of a circuit, is able to not be subjected to overvoltages of greater than 140% of normal on unfaulted phases. And this typically happens with single line to ground faults. So you've got 3 phases on the distribution system, and one of those, it has a ground fault, like a tree branch is hitting the line, or a line is down hitting the ground, something like that. In that case, the ground source is normally provided by the grid, so there's grounding throughout the distribution circuit that keeps that phase grounded, the one that's faulted, and keeps the other phases referenced to ground to neutral. And however, if you do have a fault, then you might have a switch on the distribution system open up. And then if you've got DER feeding that side of the switch, then they could be feeding the fault and energizing the other phases. And if
Yeah.
the DER...
Hey, Brian, can you hear me now?
Yes, we hear you, Tom.
I was on my phone. Everything was green, but yeah, I mean, I was on my computer, and apparently I needed to call in by phone. Yeah, so you're doing great. I mean, effective grounding really means that we're concerned that when there's a ground fault, that you get an overvoltage on the unfaulted phases. So that's what this picture depicts. And it's, from the beginning of the time when the fault occurs until it's cleared. You can see that over voltage, and systems are designed to withstand that. But we use effective grounding to keep it down to that 1.4 that you see in the note there. The problem is that effective grounding is at the substation usually. So DER then is the can, if it's islanding after you're disconnected, then it can be the source of a full 1.7 over voltage, which we're not designed for in most systems. So yeah, that's it. I think you can go to the next slide, Brian. Sorry about the audio. I can't explain it, but so here's this
no
gets a
worries.
bit
And I'm sorry to interrupt you, but since we didn't get a chance to introduce you right at the beginning, would you mind just giving a quick introduction of yourself before you continue?
Oh yeah, Tom Key. I'm at EPRI's DER lab in Knoxville, Tennessee. I'm actually at Oak Ridge National Lab today with a demonstration going on. But yeah, glad I could join this. Our full-time effort is on integration of DER these days in our lab in Knoxville. Okay, so back to the topic at hand. The transformer connection matters as far as this idea of effective grounding, and again, effective grounding meaning holding that voltage down to a level that the system is able to withstand. So there's quite a difference between inverters and synchronous machines. That's one of the important points of what we've been working on. But the other thing you do to keep the voltage down is you pick a transformer connection, and you can see in the first top line there, when you have a delta on the DER side, then it actually does provide effective grounding. In fact, sometimes if it's solidly grounded, it provides too much of a path for fault current, and so it requires some additional coordination when you add that kind of a transformer. The most common transformer used in the U.S. is the second one, the Y ground, and that allows the information of the fact that a fault's occurring. We call it a zero sequence to be passed through the transformer. Now, if you for solar systems which basically run ungrounded, that doesn't really help. If the solar keeps generating and it being ungrounded, it won't see the fault and it'll cause that over voltage. So the idea is and I think maybe 25% of the utilities require this. It used to be a little bit higher, but the idea is that the DER would provide something called supplemental grounding, a connection like the wide ground delta above, and then that would be sized, just for the size of the DER, and would be the way that the voltage is held down during that fault event. So, if the inverter trips as soon as the fault event occurs, or before, right away because of its anti-islanding, there's really not an issue, but there's not much time to make a decision. So it's still a concern for utility. And you can see the picture down below. I show some different examples of locating a grounding transformer. It doesn't have to be at the DER site. The one on top is, but you can see the other ones are, just somewhere else on the line. The problem is if the one that's on the 69 kV, if you have a fault, you're disconnected from that one. So that's why you end up needing another one further down line in order to provide that effective grounding. I think we can go on, Brian. We've or Midhat, or you're the one flipping the slides? as I mentioned earlier, and we've tried to get the standards to sort of catch up with inverters, because most of the standards originally then have been written for synchronous machines. So there's a classic one, this in the 1950s, grounding of utility systems really was basically for synchronous machines, C62.92, and so more recently, as we had a lot more inverter connections, we've updated the C62.92 to treat the inverter-based connections differently. But basically, the inverter is not as such a strong source as a synchronous machine, and so many times there's just enough, I'll call it incidental grounding in a power system. You get a line to ground connected load, and it has a similar effect to the grounding transformer. It holds down that line to neutral voltage on the unfaulted phases. So we came up with some rules of thumb that said if you have like 30% line to neutral connected load, inverters will work fine. You don't need supplemental grounding. If you installed a synchronous machine for, as a DER, then you would need it. That's well explained now in the bottom description there, the 1547.2, which, Brian, it's not out yet, right?
Right, yeah, so that's actually still there should be a P in front of that, actually, so that's a guide.
P, yeah, we
Or,
should
sorry,
have put a P
proposal.
there. It means it's almost, yeah, it's done. It's just in process. But a P means it's a ongoing project of guys working together to create the standard. It's really well covered in there. So if you get confused with all this grounding stuff, that should be coming soon. And the next slide, let's see what we're talking about. I should have checked. Is my audio okay? I was originally using.
Yeah,
Yeah.
you're sounding
Very
good.
good, Tom.
Loud and clear.
Good. Okay. All right. Thank you. Okay. Yeah, and this just mentions sort of an evolution of standards. The C62. Remember, that was that classic C62.92, and then there was dot 1, 2, 3, 4, 5, and so dot 6 is the one that we managed to get in there to cover inverters in 2017, and then we covered it again in the 1547 in our power quality section on overvoltage. There's basically a requirement so that the inverters actually can are not supposed to cause an overvoltage due to load rejection over voltage. So that gets tested. So certified inverter going forward with those that are cleared for 2018 should also help solve this problem. And we expect to see less supplemental grounding in the future. And then the dot 2, as I mentioned, is a good rundown. So the summary, I think the next slide. Are we on time, Brian?
Yeah, you're good.
Yeah. All right. So I think there's nothing new here, right? The reference to the standards. There is a screen in FERC, the small generator connection procedure for 20 megawatt and below. And the screen was kind of out of date. It was, I would characterize it as being for machines, for synchronous machines. So we're working on that. I don't know, Brian, if we're going to talk more about the updating of the SGIP in the future. The batteries project made very specific recommendations to update the small generator interconnection procedure. And this will, I think, help a lot with sort of as you make an application to connect and the supplemental review, and once the everything gets updated, it should be easier to get connected with respect to this worry for overvoltage. So yeah, I think that's it. Brian, any questions?
Yeah, I'd just add that, we do have, and we'll go into much more detail in our training next month about, recommended updates for that screen that Tom mentioned in the supplemental review, an additional supplemental review screen, which can help evaluate whether supplemental grounding is needed. And, an additional recommendation is just that those requirements should be clear in the utility handbooks because it's often a fairly murky area where developers can have trouble trying to understand exactly what the requirements are. So whether they're based on, adding supplemental grounding sources or looking towards these newer ideas of using load and evaluating that more specifically in the interconnection process, the requirements need to be clearly spelled out.
Exactly. Thank you. Yeah, sorry, I just noticed I had my video on and didn't have it facing me. So hi, everybody. Thank you.
All right, well, thank you so much, Tom, for that presentation. And we are now heading into our next round of Q&A. So I think we'll just go down, continue going down the list of questions that have been dropped in the chat box in the order in which we received them. So I think we are currently, correct me if I'm wrong, Nicole, but we are at Burke Lowry's question in the US. Do we consider the CFR a standard? And this came across during your earlier presentation, Brian.
Yeah. So Code of Federal Regulations, I guess I personally would not call it a standard. It's more of a law or regulation, more akin to the interconnection rules themselves, which are presented as rules as, generally as part of a state's regulation. This is similar, but on a federal level, I would say. So, when we're talking about the standards themselves, we're talking about something that's gone through a consensus process and through a standards development organization. Hopefully
Great,
that's
thank
clear.
you so much, Brian. All right, and I think the next question is related to 1547-2018. It was a question for Mid-Hot from Nancy LaPlaca. Nancy, if I'm referencing the wrong standard, please let me know. The question is, do you have any suggestions on how long it might take a jurisdiction to get this standard operating? A ballpark would be helpful. And Nancy, could you confirm if you were asking that in reference to 1547-2018? Yes, okay, perfect. All right, Medhat, take it away.
Yeah, so this is an item that I think it's going to be more of locations or jurisdiction specific. What we have done in the adoption decision matrix is divided those decision elements into midterm, short-term, midterm, near-term, midterm, and long-term. Essentially, the midterm and the near-term items are items you want to address before the implementation date. Now, that's going to depend on how much appetite the commission has or the stakeholder has in terms of addressing those items. Essentially, the near-term items must be done. The midterm items are items that you can pretty much rank on based on priorities. You could pick some of the items and start with those and then continue later on. The key also goes to where certified products will be, when certified products will be available. Right now, at least the theoretical date that has been out is April 1st of next year. So that's when you can start requiring this. But it's all dependent on how much appetite the stakeholders, the commission has between now and April of next year in terms of laying out the requirements.
And is it fair to say that as a general ballpark, based on what you and Brian have seen in your engagement on this issue in various states, it could be anywhere from several months to more than a year based on the variables that you just mentioned?
Yes, yeah, because depending on the groups, there could be some educational element involved. So that should be factored in. But yeah, from a few months to a year, that makes more sense.
Yeah, one year seems to be what we've seen in the past. It can be done in a year if if you're dedicated, and you know it's going to be challenging and a lot of work in a short amount of time if you try to do it in 6 months or less than a year probably. It can be
Got it.
done, but would require a lot of working group sessions in a short amount of time probably.
Yes, and a lot of staff time dedication as well. Yeah. Thank you. Thank you both. Okay, I think we'll take one more question, or actually, you know what? We are at time for questions now. Let's see how we're doing with questions. I do think I want to take one more and then we'll continue with the presentation. So Ashok asks, will IREC be working on a technical interconnection requirements document for energy storage soon? I can answer that, Ashok. So I think it's something that if you and other stakeholders feel there's a very strong need for it, it's certainly something we can look into, potentially see if we can do another partnership project like this where we're working with other stakeholders on it, but we don't have anything currently in the works. So let me ask a question back to you. Do you think this is something that we should look into?
Hi, this is Ashok. Yeah, for us at PHI is very important. Actually, I'm tasked with it. I'm going to be working on it. So I was looking out to the industry to see if anyone's working on it, which will definitely help me out. Thank you.
Good to know. Yeah, Brian and Medhat, do you have any other thoughts?
Well, I would note that the batteries toolkit does focus on the interconnection rules related to energy storage in terms of TIRs. We don't see too much difference between inverter-based, other like PV inverter-based resources and energy storage in terms of the export needs, and all of 1547 2018 for the most part, I won't say all, but for the most part is based on those export capabilities. And there are a few differences in terms of when we're talking about import, which could be an energy storage system charging. However, they are spelled out basically the same for all technologies in 1547. So there are a lot of considerations, and a lot of those considerations are spelled out in Chapter 8 of the batteries toolkit in terms of how energy storage systems and the related systems like power control systems need to be addressed, whether in the rules or in application forms and whatnot. And that's where we think a lot of those differences come into play rather than the technical interconnection requirements, although there could be some instances where you need to spell out something further about how energy storage systems are evaluated. So I agree it would be great to have better guidance in that regards, but it's probably more so on the 1547 adoption front is what we were thinking.
Great. Thank you, Brian. I was going to go look at that Chapter 8 myself based on what I've been hearing, but thank you very much.
Mm-hmm.
Yeah, and please don't hesitate to reach out with any follow-up questions, Ashok, that may come up after you take a look at the chapter.
Great. Thanks, Radina. Thank you.
Thank you. All right, so I do see everyone else who's dropped questions in the chat box. Thank you so much. We will get to them in the next break for questions. So now we proceed with the presentation, putting it all together.
Thanks, Radina. So now we've had a chance to identify the relevant standards. In this part 3, we wanted to talk a little bit more on the overlap between standards, interconnection rules, the adoption process, and how review processes can be affected by standard updates. Next slide. And we'll begin with how key standards are presently referenced. This slide is designed to give you an idea of some examples today on how such standards are referenced. SGIP and many states have a section dedicated to codes and standards. In SGIP, this can be found in attachment 3. Standards are also referenced in appropriate screens. As an example, if you look at the supplemental review in SGIP and in many other states, it references voltage and power quality related standards. Other states have a section dedicated to lab certified equipment. A good example is the Illinois 466.70. Similarly, many other states details requirement of standards, including revision years in the general requirements and definition section. This is true in Oregon and in Illinois as well. As shown, there's a diversity in practices, and what is captured here is to show you the many different sections within rules and procedures that encompasses standards. Next slide. And now, how do standards interact with rules and regulations? Here are 3 possible ways that captures how standards interact with rules and regulations. 1, you are likely to see the standards applicability in technical requirements sections within a procedure. A good example is California Rule 21. 2, some states may have technical requirements for the entire state footprint, or a utility may have their own technical requirements publicly available. Both of the first 2 options provide a means to transparently identify such requirements. There's also a third option where there just may be no available public-facing technical requirements. Next slide. So here we wanted to share an example of how the updated 1547 standards can affect interconnection process. We mentioned RPA earlier. RPA refers to reference point of applicability, which is the location where the interconnection and interoperability performance requirements that are specified in the base standard are met. Such location can affect evaluation and commissioning requirement. Per the 1547-2018, RPA location can be at the point of common coupling, PCC, at the POC, point of connection, a point in between, or could be multiple RPAs for different DI units. Agreeing on where such location is upfront can avoid unintended surprises during commissioning. So there are several things to consider before and when establishing this agreement. For small systems, do you want to establish such review and agreement in the completeness review? For large systems, do you want to agree on the RPA location in the scoping meeting? You also need to make a decision regarding whether the applicant should designate the RPA in the application form, or if you want the customer to specify that location elsewhere. Basically, to establish this designation and review properly, you're going to need to tweak some existing processes or create new ones. How are you going to handle this review will be jurisdiction specific, but given it has the potential to affect some review and timeline processes, this item should be discussed and agreed upon when adopting the new standard. Chapter 8 of the toolkit provides more guidance on this topic and gives you what I call plug and play application forms language that you can use as a starting point in this discussion. I'll turn this back to you with the next slide, Brian.
Okay. So ideally, each change to a standard would be accompanied by a certain date at which it takes effect in your interconnection rules. There's going to be a standard is established, and you might be already using that standard. Sorry. Or you need to use a new standard. course, sorry. And you need to implement that in the interconnection rules. So 1547, 1547 2018, is a new version of the standard that most interconnection rules already reference, but they may be referencing 1547 2003, or the requirements are based on 1547 2003. And really, states need to lead the way in terms of adopting these things. And it would be great, if every time there's a change to a standard, there's an accompanying change to the references to those standards, in order to ensure that everyone knows what the current rules are when they go to apply for interconnection. And there may be a need to wait some time for equipment to be available that's based on those standards. So something like 1547 2018, this is a huge change, and all the inverters for the American market are being reworked, re-engineered, and going through recertification in order to meet this. Apologize, my phone. Sorry, my phone was ringing again. Let's just silencing it. So, as stated below, in terms of implementing changes to the standards, it can take up to 18 months or longer for equipment to be updated to those new certifications. And applicants, and as well as the utilities, need to be ready to utilize those new requirements. And so then, it would be great to have an actual timeline in terms of implementing the new version of the standard, and say, there's maybe a grandfathering period, and you must comply with this new standard or this new part of the new standard by X date. That's the ideal world, and not every single change to standards necessarily requires that. But that's kind of the hope, that it's very clear in the end to the applicant exactly what requirements are required when. Let's go to the next slide. So typical stages of the adoption, and like I said, not every change to a standard is going to require everything, but for the most complex things like 1547 2018, you could utilize all these steps. So usually there's going to be some level of workshops or stakeholder engagement, which might be, or would probably hopefully be, driven by the Public Utilities Commission. And that can have educational elements to get all stakeholders up to speed about what the change to the standard is and what does it mean. And then you can create a report or comments to the Public Utilities Commission about from the working group, recommending some certain change to the rules. And then the Public Utilities Commission can put out a proposed order or decision, make sure that they understood, that report back, and understood all the issues correctly and are implementing things in the rules correctly. Stakeholders can comment on that proposed decision, and maybe there's multiple rounds of that. And then the commission issues the final order or decision. But then once that change to the rule is made, then there's implementation work, which needs to be done. And depending on the complexity of those changes, implementation may require even more workshops. And I recall when the UL 1741 supplement SA was being starting to be required in California and Hawaii, there was a lot of workshops and reports and commission decisions leading up to that date. And then there was another year of meetings on just how to implement those new requirements. And so there's not just getting the rules correct, but making sure that they're implemented correctly afterwards. Next slide. So what we would recommend generally is that the interconnection procedures and any related technical requirements should reference updated standards as much as possible. And so, when standards are updated, they should include, these processes in order to get them included in those rules. And we would also recommend that it's important to date and name those standards appropriately. And we've seen this done different ways in different jurisdictions, and not everybody includes a specific date. And so it can be challenging to understand, if it just requires conformance with 1547 itself, then you get into a gray area when 1547 is updated and you've been using the 2003 version of the standard. All of a sudden there's a new one published, and it's kind of, given the certification environment, it's impossible to comply with it right away. And so when does it actually take effect? And so having that date in there and an implementation timeline for each of these standards is important. And so you can see some examples here for the three standards that we talked about when transitioning from 1547 2003 to 2018. Those underlines are the kind of the new words in there. And then 1741 is also changing with the addition of the supplement SB for compliance with 1547 2018. Its title has also changed from the earlier versions. So having the addition in there and the date of that addition is important. And then many rules don't necessarily reference C62.92.6 as of yet. And so including that for reference for those effective grounding provisions that Tom was talking about, and including the date, of course, because that can be updated as we learn more moving forward. And I will hand it back to Midhat and Mari.
Hey, thanks, Brian. So just quickly wanted to go over what to expect in the upcoming training. So next slide. Yep. So following this workshop today, there's a training on October 13th that will go deeper into some of the topics that we discussed. This will be a 3-hour training to help us connect the dots between standards and their applicability to interconnection rules and processes. We will explore applicability of standards in processes and screens, application forms, and interconnection agreements. While we have most of the content planned out for the upcoming training, there's still time for us to make some tweaks to make sure the training matches your interest. In order to accommodate this, we would like to hear from you if there are other specific items related to DR standards that you would like to see in the training. So please help us by answering a poll question, and I'll ask Nicole, maybe she can put that in the chat. And basically it's, more details about what you would like to see, and there are options there regarding whether you want more focus on the 1547-2018 requirements, real-world example of power control systems application, more details on effective grounding, and also if you would like to get more insight on vehicle-to-grid related standards and go over the 2 or the 3 different configurations of V2G, vehicle-to-grid. I'll now turn this back to Mari.
Great. Thanks, Midhat. My name is Mari Hernandez. I'm the Assistant Director of the Regulatory Program at IREC, and I just wanted to quickly highlight some of the upcoming workshops and trainings we're planning in the coming weeks and months, just so you all are aware. So let's see. So I thought we had another slide in there on some of the topics, but maybe we skipped that one this time. So here are the dates for the upcoming workshops and trainings that have been set up so far. So after this workshop on technical standards, we're going to hold a training on grid transparency on September 26th. Then there'll be a follow-up in-depth training on technical standards on October 13th, which Midhat was just talking about. And then we're going to look at how to unlock storage flexibility by recognizing export controls, evaluating limited and non-export systems more efficiently and accurately, and allowing for system design changes during the review process in a workshop on November 1st. And it's not included here, but we're also going to be looking at doing a workshop and training on operating schedules, which is also in the toolkit.
and we'll look at some of the considerations for defining rules and processes to accommodate those types of schedules. So we're finalizing the details for some of those, so you haven't seen the invites go out for some of those, but we'll be sharing more information soon, so stay tuned for updates on that. And then we're also going to be presenting on the toolkit at RE Plus next week, Grid Forward in Colorado, and hopefully other events soon. So keep an eye on that. And next slide, please. So here is the slide I was thinking of. That was before that. These are the 8 topics that we address in the toolkit, and through webinars like this one, we're going to provide background on each of these topics and go into greater detail on how to implement the recommendations and solutions in the toolkit. So I'm not going to describe each one of them here. We can go to the next slide. And then, so a couple of our major objectives as we were developing the toolkit were that the solutions would have wide applicability across the country and be easy to use. So to that end, we used FERC's small generator interconnection procedures, which we've mentioned a couple of times. Tom talked about them too. We used those as a starting point since many states have used FERC's SGIP in their rules already. These recommendations and the model language we provide can be used by stakeholders in regulatory proceedings and working groups. And we do recognize that not all states or jurisdictions are experiencing the same level of DER penetration, and not all utilities are working with the same budget or number of staff. So we want to note that states will need to determine what makes sense for their own jurisdiction. And at the very least, you can start by ensuring that storage is included in interconnection rules and consider adopting language that would enable export controlled systems, which, as I mentioned, we'll talk a little bit more during the storage flexibility workshop on November 1st. Next slide, please. So if you have any further questions, feel free to reach out to us. We are going to go into another Q&A, so hopefully we'll be able to answer most of the questions you've had so far. And then please go to energystorageinterconnection.org to download the toolkit and find out more about upcoming workshops and trainings. And with that, I think we can go into our final Q&A.
All right, thank you so much, Mari. So once again, I'm just going to go down the list of questions that have dropped in the chat. We have a question from Taylor Spear. If at any point I mispronounce someone's name, please let me know. My apologies in advance. What tolerances are you seeing across different jurisdictions for unintentional export? That is, what times are acceptable for export cutoffs? And this looks like it was directed to Brian during the UL 1741 section.
Yeah, I can speak to that. So there's only a few jurisdictions that have really spoken to including power control systems in their rules as of yet. So California and Hawaii, Illinois, and I believe Arizona and Maryland, maybe, but I can't recall if off the top of my head now if Maryland had actually put in a specific response time for inadvertent export. So, but the standard 1741, the test protocols, the CRD for power control systems allows up to 30 seconds. That was written into 30 seconds response time was written into the earlier rules that kind of developed into our modern thinking about power control systems. And that was based in California and Hawaii's rules. And that also reflects the National Electrical Code, safety issues. And so 30 seconds is generally enough to, avoid problems with conductors and whatnot. But some utilities are just used to seeing a smaller value, like 2 seconds, in relation to unintentional islanding, or 2 seconds has been used for non-export system relay responses before. So California has kind of moved in the direction of preferring 2 seconds in a way, allowing up to 10 seconds response time. And it's actually kind of shortened from 30 seconds to 10 seconds being more the norm, with more of a preference towards the shorter end of 2 seconds. And other jurisdictions are looking more at 30 seconds and 10 seconds so far. So that's where we sit. And I think, there is a good amount of research in the batteries report in chapter 5 about how a 10-second versus a 30-second response time affects things like short-term voltage excursions. And so I'd encourage you to take a look at that. It's fairly deep technical work that's been done there, and shows that, yes, a 10-second response time is generally better for power quality than 30 seconds. However, there's no overall research that points to a need for something less than 10 seconds or for saying what the difference is between 10 seconds and 2 seconds would be. But generally it seems that 30 seconds is kind of acceptable, 10 seconds is better. And there's a question about, how much further it would need to go down. Hopefully that gets to the question, hopefully.
Great, thank you so much, Brian. Before I take the next question, I did see a comment here. I hope I'm pronouncing your name correctly. Mason, to go to the slide before the last slide. Is this the slide that you wanted to take a look at? See. Hopefully this is the correct one. Yes, okay, good. Perfect. All right. So it looks like we did skip a question here from my apologies, Drew. It seems as though Tesla has a few gigawatts of energy storage DER implemented in California. Perhaps they could help other states get with the program. I certainly agree. They definitely do a good job intervening in proceedings, in helping to shape effective policy. I think part of the challenge with everything that we're discussing today is telling the story of how utilities can trust that energy storage assets will operate as stated with an interconnection application. So there's an element of trust to continue ensuring safety and reliability, while also allowing energy storage customers to operate their assets in a way that maximizes the financial benefits to the customers and hopefully provides grid benefits as well. And so very much agreed that developers who have been successful in having their energy storage and solar plus storage assets be interconnected can lend a hand in shaping how this is done in other jurisdictions.
And I will say, since this is a standards discussion, Tesla does, help out in the development of standards, and they've got a lot of expertise in the energy storage realm and whatnot. And so, what's good for Tesla can also be good for other energy storage devices as well. But having that based on a standard that is a consensus that works for everybody is perhaps more desirable.
Thank you very much, Brian. We have a question here from Mike. It looks like it's directed to you as well, Brian, or at least it came up during your UL 1741 presentation. Mike says, our utility, DTE, seems to have an issue with field configurable settings for import and export. Are there rules about password protection of these settings, such as installer only, or does the utility control them?
So these are generally, so if we're talking about power control systems specifically, there is a level of password protection to determine what mode they can operate in, and the installers are the only ones that are supposed to be changing those. There's actually a provision for like a one-time use password in the CRD for power control systems. I think there's potentially ways we can make that even stronger in the CRD or in as it gets adopted as part of 1741, because I've also heard similar worries about whether those things are going to change. It's kind of a similar situation with relays. A relay has a ton of settings in it, and someone that has access to that relay can change those settings. So there might actually be a little bit higher level of security for power control systems which are certified versus relays, which would maybe have to be more physically controlled. So yeah, I think there's probably improvements that can be done, but there is some password requirements already included there.
Great, thank you very much. The next question is directed to Tom, and it is from Nicholas Miller. Now that momentary cessation is a very ugly word, the inverter cannot trip. Does that drive us towards grounding transformers?
So I think I'll have to try and take that in Tom's stead because I believe he had to leave.
Ah, okay.
So yeah, I don't believe that momentary cessation has an effect on the grounding requirements. Basically, what we're learning is that the potential for overvoltage from inverter-based DER is really based on how much grounded load is available, and the grounded load can provide the effective grounding for that DER when it's connected to that load in the islanded state. And it's, the DER is only going to potentially cause an overvoltage if it's actually outputting power. So momentary cessation really could help us in that regard if it's fast acting. I'm not entirely sure what you mean when it's an ugly word if you're pointing to transmission events or something like that. But in relation to effective grounding, I don't believe it has any effect on the grounding requirements of inverters. And I'd have to look to Tom to eventually back me up on that if there's a need to follow up.
All right, thank you very much, Brian. The next question is for James Brown. James, I'm not sure if you directed this towards anyone in particular, so let's see who can take it. Can inverter step-up transformers be used to regulate the voltage at the inverter terminals?
I think I can try to address that. I'm not entirely sure what that would be in relation to, but I don't think step-up transformers generally regulate voltage. They just step it. So if they could step at a certain percentage up or down. So say 1%. So that doesn't really affect exactly what voltage is at the inverter terminals or on the other side on the grid side. It's still dependent on what the grid voltage is. So I wouldn't say regulate, but it can affect the voltage to keep it in bounds one way or the other.
All right, thank you. The next question is from Drew, and it came during the Putting It All Together presentation. Drew, please fill in if I'm not characterizing it correctly. The question is, shouldn't existing be grandfathered until modified? Are you referring here to existing certified smart inverters, or are you referring to existing standards? Yes, is that a yes to inverters? Okay, yes. So Brian, I think this is the question that we had internally flagged might come up, which is it's a great question. What happens when standards are updated and let's say you have to replace your existing inverter that you already have a signed interconnection agreement for, and the new standard requires that your inverter be newly certified. What happens in that situation?
Yeah, that's definitely a question that we have flagged that should be addressed during the 1547-2018 adoption process in every jurisdiction, because it should be, and it's not just for 1547, but it would be nice to have clear procedures in terms of equipment that gets replaced to determine whether it needs to meet the existing requirements, at the time of replacement, or it just needs to meet the requirements that were in place at the time of the interconnection agreement. And we would generally say it's pretty fraught to try and make a system retroactively compliant with a standard that you don't know about at the time of installation. And so, generally we would say it's probably best practice to say that any equipment can be replaced like for like and comply with the previous standard that had complied with, but that you have an allowance to use more updated equipment. And if that equipment is updated, the utility should be notified through some process and determine whether the same settings are used or whether you can take advantage of any new capability.
Awesome. Thank you, Brian. Next question is from Lee Shaver, also came in during the Putting It All Together presentation, so that perhaps sticks with you, Brian. Given how much changed in IEEE 1547 between 2003 and 2018, it's unrealistic to expect states to simply adopt updates without a detailed review. This could change if there was a schedule of updates for IEEE 1547, similar to how energy codes are updated on a 3-year cycle. Is this possible?
Yeah, well, I think one reason it's so complicated with the transition from 1547 2003 to 2018 is because of that huge 15-year gap. And so we would hope, and IEEE is targeting more updates of a shorter time span. I don't think there's an exact cycle targeted at the moment, but probably a 5-year cycle or something like that is more possible. Generally the development can take a little while. We're just barely starting to learn anything about 1547 2018 because it hasn't been implemented anywhere as of yet. And so we actually are starting the development process at the end of this year or at the beginning of next year to start revising 1547 for the next revision, but that usually takes at least 2 or 3 years in itself. So it's probably not a 3-year cycle, but we'll probably be looking at shorter cycles moving forward.
All right, thank you very much. And I think we've got time for one more question. Any that we don't get to during the Q&A, we'll see if we can follow up with you folks via email. And I'm sorry, it looks like we missed a question that was previously plugged in during the Q&A section. This is from Benedito Bonato. Assuming that all the standards are concluded and available, would it be enough to consider the challenge of integrating DER sustainably, protectively, and supportive to the grid stability during hard contingencies? How quick and how slow can the DER be islanded?
I don't know if we can get to that in 1 minute or not, but let's see. Assuming all standards are concluded and available, would it be enough to consider the challenges of integrating DER sustainably, protectively, and supportive of the grid during hard contingencies? I mean, I think we can. I'll just to try and wrap this up on time. I think we can say, yeah, there's further work to be done in terms of improving grid supportive technologies that might not be acceptable today or maybe not be imagined to become in wide use yet today. We do want the standards in place, and I think things are moving, and they will be moving through the standards development process to get there eventually. I think that's probably as best we can say about that.
That's great. Thank you so much, Brian. And I think what we can actually do is, I know Midhat said earlier that we are putting a call out for questions and topics to address during the training. So we're very happy to flag remaining questions that perhaps we can weave in there. I'm sorry we couldn't get to all of your questions. Thank you for being with us today once again. Really appreciate it. Hope this has been informative. And if you have any further questions that we can answer for you, you can reach out to myself or to Mari. And we look forward to you joining us for future trainings.